Hi everyone. Firstly, we would like to thank the committees for the opportunity to present our work here and for the organized structure provided for us. This is really a landmark, which made us choose ISDA 2017 to submit our paper. Our paper is entitled as A Comparison of Machine Learning Methods to Identify Broken Bar Failures in Induction Motors Using Statistical Moments. We are part of the academic master's degree in renewable energy in the Federal Institute of Education, Science and Technology of Ceará, located in Brazil, state of Ceará. The authors are Neiver de Medeiros Mendonça e Nascimento, a Master of Science student, Claudio Marques de Samedeiros, Ph.D. and Pedro Sarabaucas Filho, Ph.D. This presentation is divided into introduction, wherein we are going to present the justification and basis to conduct our research, followed by the steps explanations and the methodology. Then, our results are going to be shown, leading to our conclusions. It is estimated there are more than 300 million electric motors all over the world, consuming 7,400 terawatts-hour, which represents 40% of global electricity production, and Brazil highlights it because 70% of industrial electric consumption is due to electrical motors. And research presented by Bonnet compile 40 years data exhibits the broken rotor bars represents 5% of total failures. Vibration signals have been widely used for failure analysis in rotational machines. At first sight, this might not be such a representative percentage, however, due to the total number of electric motors, 300 million, even a small percentage account for a large number of equipments. So the broken rotor bars should not be overlooked. During a review on literature, we found related and relevant works, such as presented by Martinez et al., wherein was proposed theoretical equations for vibration patterns in electrical motors during abrupt broken rotor bars. Its works provide a mathematical fault index value. That is not the focus of our work. We aim to build a fault identification system based on machine learning. And we also encountered papers indicating the higher-order statistics, HOS, as a promising technique to describe time domain signals, and researchers have directed their attention for HOS as an auxiliary tool for fault detections on rotational machines. So, our focus is to combine both higher-order statistics and machine learning in order to identify broken bars in SQUIRELL cage induction motors, using vibration signals. Our methodology consists in 3 major steps: a data acquisition, where we simulated the induction motor in 2 basic conditions, normal and faulty. Then, in a pre-processing phase, we conducted a signal segmentations and feature extractions using higher-order statistics, and we performed classification takes via machine learning methods, specifically naive Bayes, OPF, SVM and MLP. In our experimental setup, we used a 3-phase induction motor, 1 CV power, wired in delta, 220 volts, powered by a frequency converter CFW08, under 30, 35, 40, 45, 50, 55 and 60 Hz, on 3 different operating conditions, on load, 50% and 100%, through the eddy current break. We also used MEM's accelerometer, MMA7361L, acquired by the National Instruments Data Acquisition Module, USB 6009. Each experiment was performed while the machine on steady state, during 10 seconds, with a 10 kHz sampling rate, and the outcome is 100,000 data points. Here we are going to explain the pre-processing step. The data provided by the sensor is a 3-axis vibration signal, which are forward split into 5 parts, then kurtosis, skewness and variance are calculated for each axis. The results are a 9 features sample. There are 21 assays for normal operations and 21 for faulty operations. At the end, we created a dataset with 210 samples and 9 features. Now, we are going to present our results. SVMP and SVMR have achieved the maximum accuracy, sensitivity, specificity and F-score values, demonstrating itself to be an effective approach to identify broken bar in three-phase induction motors. However, other methods have gotten near to SVM-P/R, like MLP2, SVML, OPFM, and naive Bayes. Besides the simplicity, less number of parameters to be adjusted during training, naive Bayes was able to classify 100% of normal and faulty conditions correctly in its best training. Therefore, MLP1 obtained the worst average accuracy and a higher variance, which indicates a poor capacity for detection. Either the motor is operating in normal or faulty condition. All methods were able to identify each class correctly, but naive Bayes, SVML, SVMP, SVMR and MLP2 have demonstrated to be more sensitive to identify changes in vibration patterns caused by broken bars and squirrel cage rotors. MLP2 is both sensitive and specific to identify normal and faulty vibration motor patterns. The three OPF methods have reached similar results, but the Manhattan distance provided lower variance, resulting in more stable classifications. The training time, TRT, testing time, DST, for all methods are shown in Table 3, alongside with its accuracy. As expected, MLP1 and MLP2 took much more time than other methods because of its recursive training process based on backpropagation and gradient descent. They were followed by SVMP, that indicates, regards its accuracy, the polynomial kernel might not be suitable. The OPF-E/G and M had much faster training than MLP and SVM, due to its graph reorganizing theory and fast distance computing, compared to backpropagation, i.e. MLP, and inverse kernel matrix, i.e. SVM. But the faster method, among those, were naive Bayes, essentially because its batch learning mode through a simplified covariance matrix. On the other hand, MLP was faster than other methods, because it only requires linear algebra operation as long as properly trained. This research made us possible to conclude that the higher-order statistics has demonstrated to be an effective and powerful tool to identify pattern in vibration data from three-phase induction motors. From the tests conducted with MLP, it is concluded that as number of hidden neurons pass 10, the accuracy decays due to overfitting. And MLP2, i.e. 8 hidden units, was far better than MLP1, i.e. 5 hidden units, in all metrics, especially because it has shown less dispersion in classification, indicating to be a more stable classifier. Since there were not applications using electrical machine alongside with OPF, we have evaluated its performance and reaffirm what Popper et al. 2010 suggest, that OPF is faster than MLP and SVM and possible to achieve similar or better results. Thank you all. We appreciate our attention and are more than welcome to respond to any further questions. Please let us by emailing at us and links provided.